Imagine you're standing right in the middle of a perfectly gridded city.
Like the quintessential Manhattan street layout.
Exactly. Concrete canyons, perfect 90-degree intersections everywhere you look,
Mm-hmm.
and you're completely uncaffeinated.
A dangerous state to be in.
Very. So you pull out your phone to figure out which of three different coffee shops is technically closest to you.
Right.
Now, if you were a bird, this would be an incredibly trivial math problem. You just fly in a perfectly straight line over the skyscrapers directly to the nearest espresso machine.
Right. The classic is the crow flies distance.
Exactly. But you can't fly. You're on foot.
Yeah.
You are physically bound to the concrete sidewalks, forced to take sharp right angle turns around these huge city blocks.
Which completely changes the math.
It does. So the question is, how do you mathematically draw a map that perfectly defines who is closest to what when you are entirely restricted to moving on a grid?
It's fascinating because it changes the rules of geometry from the ground up. I mean, when you strip away the ability to travel diagonally, the traditional ways we measure distance and define territorial boundaries, they just disintegrate.
They completely stop making sense. So, okay, let's unpack this. Welcome to today's deep dive. We are venturing into a really fascinating, highly practical corner of computational geometry.
It sounds intimidating, but it's super relevant to daily life.
Oh, absolutely. We're pulling from a set of slide decks that detail something called rectilinear Voronoi diagrams. And our mission for this deep dive is to understand how we can perfectly partition a grid-based world.
We're going to get into a brilliant algorithm from 1980 by Li and Wang.
Yeah, and uncover why this specific flavor of math is like the secret sauce behind everything from automated warehouse robotics to the microscopic chips inside the device you are listening to right now.
We are essentially bridging the gap between abstract mathematical theory and very rigid physical reality. We're taking pure math and forcing it to obey the rules of the pavement.
Right. And to set the stage, we should probably establish what we are actually trying to draw. A Voronoi partition, for anyone who hasn't encountered one lately, is basically just a way of dividing a plane into distinct regions based on a specific set of target points.
And we call those target points sites.
Sites, right? So in the coffee shop example, the 3 cafes are your sites. The golden rule is that every single coordinate inside a specific region is strictly closer to that region's site than to any other site on the entire map.
You're drawing an absolute territory map. So if you are standing anywhere inside Cafe A's region, you are mathematically guaranteed that Cafe A is your shortest walk.
But here is where we hit the friction. We're so used to plotting these maps using Euclidean distance, the classic L2 metric.
Which relies on the Pythagorean theorem.
Right. You draw straight lines, calculate the hypotenuse, and when you map out the boundaries of all points equidistant from a center site, you get a perfect, smooth circle.
But as we established, you and I aren't crows.
No, we are not. The Pythagorean theorem is completely useless to a delivery driver navigating a high-rise grid.
Well, because the physical world often dictates the math, not the other way around.
Yeah.
We have to abandon L2 and switch to L1 distance.
Widely known as Manhattan distance, right?
Exactly. In L1, distance is simply the absolute difference in the x coordinates plus the absolute difference in the y coordinates.
So just how many blocks east plus how many blocks north.
That's it. That is your total distance.
I look at this as the ultimate metric showdown. But I mean, if straight lines are inherently shorter, it feels bizarre to handicap ourselves. Why force the algorithm to take the stairs when Euclidean math is so well established?
You have to look at the constraints of the physical systems we're programming. You cannot drive a delivery truck diagonally through a high-rise apartment building.
That would be bad.
Very bad. Think about a robotic arm in a massive automated warehouse. It moves along ceiling tracks that run purely on rigid X and Y axes. If you use L2 Euclidean math to tell that autonomous robot which charging station is closest, the algorithm might calculate a beautifully efficient straight line path.
Right through a solid steel rack of inventory.
Exactly. It would crash immediately. L1 distance forces the algorithm to perceive the spatial world the exact same way the physical object has to navigate it.
Which radically alters the visual geometry. I mean, if you map all the points that are an equal L1 distance from a center site, your boundary isn't a circle anymore.
No, it's a diamond.
Yeah.
Basically a square rotated by 45 degrees.
And that shifted geometry means the boundary lines separating these territories, the bisectors, behave in ways that might feel entirely alien compared to traditional freehand geometry.
Yeah, let's get into the anatomy of that L1 bisector, because if the circle is now a diamond, the border walls between territories must look incredibly strange.
Right, because in the Euclidean world, a borderline between 2 points can angle in any conceivable direction. 30 degrees, 72 degrees, whatever perfectly splits them.
But in the L1 world, we are completely locked to the grid. The lines are strictly constrained.
So what are the actual options?
An L1 bisector can only exist in exactly 4 alignments: 0 degrees, 45 degrees, 90 degrees, or 180 degrees.
Wow, so no smooth curves.
None. And no arbitrary slopes either. They form convex polygons with strictly axis-aligned edges.
It's like drawing boundaries with an Etch-a-Sketch instead of a freehand pencil.
Mhm.
You only get perfectly vertical, perfectly horizontal, or perfectly diagonal stair steps.
That is a perfect analogy.
But how does the math actually know which one of those to draw?
The engine behind it is actually incredibly straightforward. It's a pure comparison of gaps.
Okay, how so?
To find out what kind of line divides 2 points, you just compare their x distance to their y distance. If the x distance between 2 points is greater than the y distance, the bisector is forced to be a vertical line right down the middle.
Let me visualize that. So if Cafe A and Cafe B are 10 blocks apart horizontally, but only 2 blocks apart vertically.
The horizontal gap is the dominant separation.
Right, so to divide them fairly, you have to drop a vertical wall straight down between them.
That's the logic. And conversely, if the y distance is greater, the bisector drops in as a horizontal line. The grid forces the boundary to run perpendicular to the largest gap.
Okay, I follow that.
Yeah.
But what if neither is the largest gap? Let's push this into a corner.
Uh-oh.
Yeah, what happens if 2 sites are in a perfect diagonal configuration? Like where the x distance and the y distance are completely exactly identical. Does the Etch-a-Sketch just snap in half?
You've just stumbled into the exact scenario that keeps computational geometricians awake at night.
Really?
Yeah. You were describing the degenerate edge case. The literature calls it the square bisector ambiguity.
Oh, computers absolutely despise ambiguity. So what actually happens on the map?
Well, in Euclidean math, a bisector is always a crisp one-dimensional line no matter where the points are.
Right.
But in L1 math, when the absolute difference in x perfectly equals the absolute difference in y, the bisector stops being a clean line entirely. It inflates.
It influences.
Yeah, an entire two-dimensional square region emerges between the two sites. And mathematically, every single coordinate inside that entire square is exactly equidistant to both sites.
That is wild. It's like a massive zone of pure mathematical indecision.
Exactly.
The algorithm basically looks at this whole city block and says, take your pick. Both cafes are the exact same number of footsteps away.
But we can't have overlapping territories in a Voronoi diagram. The primary rule is that every point has to belong to exactly one site.
Right. So how on earth do programmers fix a broken dimension like that?
They rely on a clever, somewhat brute force workaround called point nudging.
Point nudging.
Yeah. The algorithm doesn't just blindly start drawing lines, it iterates through all the data points first.
Right.
If it detects that a pair of sites has exactly equal x and y distances, meaning they're about to generate one of those ambiguous squares, it steps in and perturbs one of the points.
Wait, it just alters the data. It literally moves the coffee shop.
It does, but by an infinitesimally microscopic amount. The code takes a tiny value, say, multiplying the coordinate distance by 1 times 10 to the negative 10th power, and adds that microscopic fraction to one of the points.
So it's so small that it has absolutely zero impact on the physical accuracy of the real-world map.
Exactly. You wouldn't even notice it on a molecular level. But mathematically, it completely eliminates the equality. The x and y distances are suddenly just slightly different.
So it forces a clean bisector line to form.
Yeah.
I love the sheer pragmatism of that.
It's very practical.
It's like a mayoral election resulting in a mathematically perfect down to the last ballot tie. Instead of leaving the government deadlocked, the election officials look at a microscopic fraction of a variable.
Like who technically handed in their ballot a millisecond earlier.
Yes, just to forcefully tip the perfectly balanced scale, avoid the paradox, and declare a clean winner.
That's a great way to think about it. Point nudging forcefully tips the scale just enough to keep the geometry clean.
Okay, so we now know how to draw a single boundary between 2 points without ripping a hole in the space-time continuum.
Right, but a real map doesn't just have 2 points.
No, a city has thousands of intersections. A microchip has millions of microscopic transistors. We cheated to fix 2 points, but how does a computer process a million points simultaneously without just grinding to a halt?
That brings us to the actual computational engine. If you want to process massive data sets, You rely on Li and Wang's 1980 divide and conquer algorithm.
Okay, Li and Wang.
Yeah, it boasts an optimal theoretical efficiency of ON log n.
Now, I always try to look at these algorithms from a naive perspective. Why do we need a complex sorting algorithm at all? Like, if I have a million transistors, why not just write a script that measures every single point against every other point from the start?
Just brute force the measurements.
Yeah, exactly. Just calculate them all.
Well, it comes down to exponential logjams. If
Yeah.
you only have 10 points, comparing everything to everything is easy. 100 calculations, no problem for a modern processor. But if you have 10 million delivery drone hubs, a brute force approach means you are asking the computer to perform 100 trillion comparisons. The workload grows exponentially and just crashes the system.
Oh, wow. Yeah, that's a problem.
Li and Wan's divide and conquer method bypasses that completely. It doesn't compare everything to everything. It uses a strict 4-step process to drastically cut down the workload.
So let's look under the hood of those 4 steps. Step 1 is the split.
Right. First, the algorithm takes all the input sites and sorts them purely by their x-coordinate, scanning from left to right.
Okay.
Then, it recursively slices the data set in half right down the middle over and over again. It builds a massive tree, isolating everything until it reaches tiny atomic base sets of just 1 or 2 points.
Which sets up step 2, the base case. Because we know how to deal with 2 points.
Exactly. We just spent the last few minutes outlining it.
Right. The algorithm computes the direct L1 bisectors for those tiny simple pairs using our Etch-a-Sketch rules and nudging them if they tie.
Spot on. And once those simple hyperlocal borders are drawn, we hit step 3, which is the merge. This is where the heavy lifting happens.
How so?
The algorithm starts working backward up the tree. It takes those tiny isolated maps and stitches them back together to form larger and larger unified territories.
But merging borders has to be a nightmare. I mean, if you push 2 separate territorial maps together, their boundary lines are going to crash into each other.
They absolutely do.
Old borders are going to be invalidated by the new, larger layout, which I assume sets us up for step 4, the hardest part of the entire system.
You guessed it. Step 4 is the walk. When 2 subdiagrams merge, the algorithm has to literally trace or walk the newly formed boundary lines separating the left map from the right map.
Like physically trace it?
Yeah, it uses a highly specific loop structure to pull this off. As it traces the new jagged merge line, it is constantly scanning for intersections where the new border crashes into an old bisector.
I picture a tiny surveyor walking the property line with a laser level, just constantly checking for overlapping fences.
And when it finds an overlapping fence and intersection, it updates its reference of the current site. But the real magic is the virtual scissors.
Virtual scissors.
Yeah, when a new border supersedes an old one, portions of the old boundary lines are suddenly trapped on the wrong side of the new wall. They are dead ends, orphaned regions.
Oh, I see.
So the algorithm uses a trimming function to crop those old lines exactly at the intersection point, permanently deleting the trapped orphans so the map remains perfectly clean as it grows.
It's just endlessly pruning the overlapping branches as it scales up the map.
Precisely.
But practically speaking, how does a computer physically remember which line got cut? I mean, if you're doing this millions of times, recursive splitting, merging, virtual scissor trimming, the underlying data architecture has to be unbelievably rigid.
It has to be. Or the computer will just lose its place and delete the wrong borders.
Right.
It requires a meticulously organized, object-oriented blueprint. The source material outlines the 2 core interacting data classes required to keep the system stable. First, you have the site class,
Which is like the central hub. It tracks the basic X and Y coordinates, but it's doing a lot more than just holding a location, right?
Way more.
It also maintains a dynamic list of all the bisector boundary lines attached to it, calculates the final vertices of its polygonal cell, and keeps active pointers showing exactly who its neighboring sites are.
It acts as the anchor for the territory. Now, the second piece of the architecture is the bisector class. This object represents the border walls themselves.
Okay.
It tracks the 2 parent sites it divides, its own start and end endpoints, and the exact coordinates where it intersects with other lines. But crucially, and this gets to your question about how it doesn't get lost, it tracks its own depth in the recursion tree.
Wait, why does a line care how deep in the tree it was born? Like, why is its age relevant?
Because of the merge phase. When 2 territories crash into each other and the virtual scissors come out, the algorithm needs a hierarchy.
I think I see.
It needs to know which line was drawn first, at a lower level of the tree, to correctly determine which line gets clipped and which one remains intact. Tracking the depth prevents the algorithm from accidentally deleting a massive regional border instead of a tiny local fence.
That is incredibly elegant. It builds its own historical hierarchy to avoid overriding itself.
It really is.
But, even highly optimized engines have limits. What happens when this algorithm hits a wall?
Well, the diagnostics reveal a few key constraints. First, despite the ON log n efficiency, pure computational performance does begin to degrade when you process more than 100 points in a single unoptimized batch run.
Really? Just 100?
Yeah, the recursive overhead simply starts to add up. Additionally, specific collinear configurations, meaning multiple sites lined up in perfectly straight horizontal or vertical rows, can cause traversal issues during that complex walk phase, confusing the intersection scans.
That makes sense. If everything is perfectly aligned, it might glitch out.
Right. And finally, the algorithmic output often generates duplicate boundary vertices, which means you have to run an extra post processing cleanup step just to tidy up the data before you can actually use it.
Even with those constraints, the structural output is fascinating. I actually loved this specific diagnostic statistic from the sources.
Oh, the 8 points one.
Yeah, they ran a sample map with 8 random points, and the geometric distribution of the resulting boundaries was perfectly balanced.
It's so clean.
35% of the edges were horizontal, 35% were vertical, 20% were those 45-degree diagonals, and the remaining 10% were complex connection nodes. It perfectly mathematically reflects the rigid constraints of a city grid.
It mirrors the environment it was built for. And, that brings us to the ultimate synthesis. We've built this massive engine, we've used point nudging to fix the ambiguous glitches, we've structured the data into rigid classes to survive the recursive merging.
Right.
But why does all this matter? Why does L1 Manhattan distance ultimately win out over straight line math in the real world?
Yeah, what's the massive advantage for your daily life as a listener?
It basically comes down to three massive operational advantages. First, computation speed. Because L1 math only uses absolute addition and subtraction, it entirely avoids heavy square root calculations.
Which takes an enormous burden off a computer's
A
process.
huge burden. Second, those axis-aligned boundaries we just talked about perfectly map onto the pixel structures of digital screens and the rigid grid layouts of hardware sensors.
Oh, that makes perfect sense.
And third, it provides superior interpretability for physical systems.
The math actually speaks the language of the physical world. And you see that in the staggering list of real-world applications in the sources. I mean, it's heavily used in urban planning to calculate facility locations and optimize delivery zones along street grids.
Yep.
It's how cellular networks map tower coverage zones, so your phone knows the precise invisible boundary line of when to drop one signal and pick up the next.
It's foundational in robotics, too, specifically for path planning and sensor coverage in massive warehouse matrices. It ensures that a fleet of autonomous forklifts can perfectly share space without ever crossing paths.
Yeah, and it goes even smaller than that. It is deeply embedded in VLSI design, which dictates wire routing and component placement on microscopic silicon microchips.
It's everywhere.
It's used in image processing for pixel segmentation and even in game development to procedurally generate massive digital worlds that don't constantly crash the physics engine.
When you step back and look at that list of applications, you realize that the modern world is fundamentally built on rigid grids. From the microscopic silicon pathways packed into our laptops to the massive, sprawling city blocks we live and work on,
Yeah.
L1 Manhattan distance isn't just a quirky, stair-stepping alternative to standard geometry. It is quite literally the native spatial language of human infrastructure.
That is a phenomenal way to frame it. So let's recap the journey. We started by throwing out our Euclidean circles and trading them in for L1 diamonds.
Goodbye, straight lines.
We learned that when the math gets paralyzed by an ambiguous square tie, we can literally nudge the data a fraction of a millimeter to save the universe.
Point nudging for the win.
And we saw how Li and Wang leveraged a massive recursive tree to divide, conquer, and perfectly map out our complex grid-based reality using virtual scissors and object-oriented blueprints.
It is a brilliant testament to how creative computer science has to be just to mirror the constraints of the physical world. And, it leaves us with a really compelling thought to explore moving forward.
Oh, what's that?
We've spent this entire time talking about the two-dimensional grid cities, microchips, warehouse floors. But consider what happens when we look up.
Up into the air.
Exactly.
Hmm.
As our physical world pushes into the three-dimensional airspace with drone delivery swarms or down into the oceans with subaquatic mapping networks, we are leaving the flat grid behind. The z-axis introduces an entirely new realm of L1 complexities and ambiguities. It makes you wonder, as human infrastructure breaks free from the two-dimensional pavement, what entirely new computational geometries are going to have to be invented just to keep our future automated world from crashing into itself.
It's a spatial puzzle we are only just beginning to solve.